You never want any bad actor to be able to shut down your BPF programs, because no matter how secure your BPF programs are, if someone can just shut them down, then your BPF programs no longer exist, which means they are essentially useless. So to understand this attack vector and to actually secure against it, let's look at a normal BPF program. So I'm going to run bombfather with no config. So this is just an example BPF program. This should work for any BPF program. So I'm also running it, as you can see, with no config. So it's just running and it's sitting there. So as a bad actor, if we just get the PID of this agent, and I run sudo kill-9, I'm able to kill the agent and it's dead. Now, this attack does require elevated privileges. If you want to shut down a BPF program or any process, you either need to be the owner of that process or you need to be root. Now, this may seem infeasible, right? How will an attacker get root access on your system? But it is possible. If they can breach your system and get access to your system and then use a privilege escalation attack, something like NVIDIA Escape or attacks on sudo itself, which really do happen, then they can potentially get root access on your system. And if this is a possibility, we ideally would want our BPF programs to be able to stop this and thwart these root level attackers. So what can we do? Well, what we can think about is we need to make sure that no one can send a kill signal to our BPF agent. And we can stop this with BPF. You see, we can write a BPF LSM hook security task kill to basically limit all kill signals to our bombfather or BPF agent. And that's exactly what I can do right here. We'll get into what the other stuff mean right now, but essentially this is just writing a hook on security task kill. So if I run my bombfather agent, we can get the PID of our agent, and we can run sudo kill-9 on that agent, and we can see the operation was not permitted. And we can also see we registered the kill attempt. That was because we are now hooking into that BPF LSM hook, and now we're able to stop all of these attacks. So our job is done. That's pretty simple. But what happens when I need to upgrade our runtime system, right? This is some sort of BPF deployed solution, and there's a new feature that's added that we want. So I need to restart and essentially stop my bombfather agent. So to do that, I try to kill it, but it doesn't work. What do we do, right? We can't shut it down. It's not just sitting there, and we can't do anything to it. We can't upgrade. If there's some necessary change we need to make, we can't do anything. So at the end, you'd have to really restart your system. We'd have to restart all the nodes that are running this BPF program and remove this feature because it's stopping us from really moving ahead with any development. So we need a way to somehow differentiate between actors that are good actors, right? We're trying to shut down our BPF program, and bad actors. But we can't even trust sudo. So what can we do? Well, what we can do is use cryptographic signing. So let me just go over to this note. So let's say we have our actor. We don't know if they're good or bad. And we have our BPF program, right? And we have a server. Now, essentially, if our actor can sign some sort of message, send it to our agent, and our agent verifies that message is good, it's signed by some sort of authorized by some sort of authorized key, and then then it will just say it's shutting down and it can kill itself. Now, we're using private keys, and we can trust them more than sudo because we can export security from the target system to another system. So for example, let's say we were using a hardware wallet to store that key. If our actor wanted to shut down our agent, they could query and send a message to the human who held that key. That human could sign a message with that private key on that hardware wallet and send that signed message back to the actor. And then the actor could send it to the agent. Essentially, we can really force human in the loop for these high value situations. But this does have an attack vector. You see, the BPF agent doesn't care what message is being signed. So if a bad actor can somehow get access to that signed message, then they could replay that message in a replay attack. Where, again, if they get that signed message later on, whenever they want to, they can send that signed message to the BPF agent and shut it down. And if we don't want to do some sort of key circulation, that's not really something we want to do, then how can we deal with this attack vector? Essentially, we can use nonce-based shutdown protection. So we add an extra step. We first request a random string, and that is a nonce. We get that nonce, and that also pushes this nonce to like a temporary database inside our agent. Now we have this nonce, and we can essentially sign that nonce and send it back to the agent. The agent now verifies that nonce has not expired. We get rid of each nonce after 5 minutes, and the nonce is signed by a valid signature. And then we can just shut the agent down. This essentially forces the re-signing of every single time you want to kill a BPF agent, so that no one can run a replay attack. So what we can do now is we're going to run this stop.sh command, which essentially just hits those API endpoints and signs it with a good key. So, and we can see we have on port 8089 with this public key. So if I run .stop.sh, we can see that the shutdown was initiated and Bonefather killed itself. And if I turn this into a bad keys private key and I run this agent again and we try to kill it, we can see the signature verification failed. We got this nonce, we tried to sign it, and it failed. So, if we want to be running secure BPF applications at a really high level, we ideally need some sort of shutdown protection for these BPF agents, because it's much easier to just shut them down versus trying to sabotage BPF itself. Thank you for watching.